Okay, so our next topic is the topic of determinants. In this topic, I'm going to be even more than previously. I'm not going to prove almost anything. Okay, it's really going to be a survey of the topic, how we work with determinants. We really consider it as a tool and pay less attention to its theoretic value. Okay, so I'm gonna define determinants inductively. So I'm going to start with n equals 1. Okay, determinants are only defined for square matrices. Okay, so if n equals 1, it means that A is just has one entry. That's a 1 by 1 matrix. Do you agree? Okay, and then by definition, the determinant of A, which is denoted with two bars like this, just like absolute value for numbers, is just the number, the single number A sitting in the single entry of the 1 by 1 matrix A.
What is that notation again?
That's the determinant. Okay? So this is in definition, an inductive definition. Okay? So for n equals 1, it means that the matrix is a 1 by 1 matrix, and the determinant, denoted like this, is just the number. I'm going to write the formal definition in a minute. What if n equals 2? Then A is a 2 by 2 matrix. Let's call it A, B, C, D. That's A in general. And the determinant of A is defined to be A, D minus B, C. Okay? And you have to look up here a second. Look up here. A, D minus B, C. A, D minus B, C. That's how I remember it. A, D minus B, C. Good? Okay, so now we know what a determinant for a 2 by 2 matrix is. Let's pause for a brief example. Suppose A is the matrix 5, 6, 8, 9. What is the determinant? And note that for the determinant, I should write the bars, and inside the bars, the parentheses. But it's usually written without the parentheses. These bars kind of lay the barriers for the matrix anyhow, and it's just written like this. So the determinant of the matrix 5, 6, 8, 9 is 5 times 9, 45, minus 6 times 8, 48, which is negative 3. That's the determinant of this matrix. Good? Okay. Moving on, for n equals 3, so I'm not going to write A, B, C, D, E, F, G, and so on. I'm going to start labeling them like we usually label entries. So A is now A1, 1, A1, 2, A1, 3, A2, 1, A2, 2, A2, 3, and A3, 1, A3, 2, A3, 3, right? This is a general 3 by 3 matrix. What is the determinant? So I'm going to move on to the next board. So the determinant of this matrix, A1, 1, A1, 2, A1, 3, A2, 1, A2, 2, A2, 3, A3, 1, A3, 2, A3, 3. And you're probably thinking, is he going to do this for n equals 4 now? No. So we're going to understand the idea for 3, and then going to write it for a general n in an inductive manner. And so the determinant in the n equals 3 case is going to be based on the determinant in the n equals 2 case. And okay, so what is this determinant? So here is what I do. Here is how it's defined. I take the first entry here, A11, cross out its row and its column. I'm left with a 2 by 2 matrix. And I take the determinant of that, A11 times the determinant of A22, A23, A32, A33. So I took A11, crossed out its row and its column, and multiply it by the determinant of the 2 by 2 matrix that's left. Minus, I take A12, and multiply it, cross out, you have to look up here a second, cross out its row and its column, that's this T here. I'm left with a 2 by 2 matrix, take its determinant. A21, A23, A31, A33. Good.
We use it in physics.
Yes, the determinants are used in many places. For example, in physics, in Jacobians, when you do change of variables, there are many places where these things show up. Okay, and so if they're familiar, that's good. Plus, I take the last entry in the first row, namely A13, cross out its row and column. I'm left again with a 2 by 2 matrix, take its determinant, which was defined earlier. Good? So that's how the determinant is defined for a 3 by 3 matrix. Okay? And now each of these, I can do another step by writing what these are. Okay? Because what are these? This is A22 times A33 minus A23 times A32. But that was previously defined. I don't need to do that. Okay? And in particular, I don't need to remember things. I don't need to. You can open this up and get a bunch of expressions, each of which is a product of 3 of these little a's, but you don't need to do that. Okay? You don't need to remember something very complicated like A11, A22, A33 minus A11, A23, A32. Do you see why I'm doing what I'm doing? You don't need to remember this. You just need to remember the method. You take the first row, each element multiplied by the determinant of a lesser n, where you crossed out its row and column. And then take interchanging signs, plus, minus, plus. And if it were a 7 by 7 matrix, minus, plus, minus, etc. Okay, that's the idea. So first of all, let's do an example to see that we're on top of things. So what's the determinant of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9? What's the determinant of this? So it's going to be 1 times the determinant of 5, 6, 8, 9. 1 times this little determinant minus, interchanging signs, 2 times 4, 6, 7, 9 plus 3 times, cross out row and column, 4, 5, 7, 8. Good? Is it clear what just happened? I took the first row, took its elements, each of which I crossed out its row and column and multiplied it by the 2 by 2 determinant that remains after this crossing out business. Okay? We're going to have some terminology and notation for this stuff in a minute. And now I want to actually calculate the determinant, so I have to go through the process. I have to calculate it. So it's 1 times 45. Let's write it. 1 time, I know, but let's write it nevertheless. 45 minus 48. Minus 2 times 4 times 9 is 36. Minus 6 times 7 is 42. Plus 3 times 4 times 8 is 32. Minus 5 times 7 is 35. Do you agree? Good? And this equals minus 3. This is minus 6 times minus 2 plus 12. And this is minus 3 times 3 minus 9. And in fact, we just get that the determinant of this matrix is 0. Good? Did everybody follow? Clear? Okay. So first of all, a definition. What we did here was we took a row and took a column and crossed them out. whenever we do that, we're left with a matrix which has n minus 1 rows and n minus 1 columns. Okay? So that sort of matrix is called a minor. That's the terminology. So this is the minor corresponding to 1, 1. The number is the number that you crossed out the row and column and got left with it. Okay? So in general, here's a definition. The determinant of a matrix obtained by eliminating the ith row and the jth column of a bigger matrix of A is called the ijth minor of A, and denoted, so there's even notation here, M sub ij. Okay? So, for example, let's go back to the calculation that we just did. This, for example, this thing here, how did we obtain this? We crossed out the first row and the second column. So that thing is M1, 2, this determinant, the determinant of this 2 by 2 matrix. So this thing is M1, 2 in this example. Is it clear? And what would this thing be? Right, M1, 3, because we crossed out. And this is M11. Here we only have the minors corresponding to the first row. They all start with 1 because that's what we said we're doing. We're taking the elements in the first row, crossing out rows and columns, and being left with minors. Clear? Okay. So another way of writing this thing, tell me if you agree now, another way of writing this thing, maybe let's write it up here in blue. So this thing equals, right, A11 times M11 minus A12 times M12 plus A13 times M13. And each of these m's is of a one row and column missing. It's an n-1 determinant where we started with an n by n determinant. Clear? Okay. So do you agree that this is a short way of writing this now that we have this notation? Notation is a very powerful thing in mathematics. Very powerful. Okay, good. So now we can define the determinant for a general n. Definition. The determinant of a n by n, it's only defined for a square matrix, denoted by vertical bars, is the determinant of A equals A11, that's the first element in the first row and first column, times M11. And M11 is going to be the determinant of a matrix of size n minus 1 times n minus 1, right? Minus A12, M12. Plus A13, M13. And so on. When it was a 3 by 3 situation, this is where it ended. In general, there's going to be minuses and pluses here, all the way until you get to minus 1 to the power n. So we want a plus when n is odd. So n plus 1 times m1n. That's the last minor. Do you agree? Oh, I forgot. A1n. Sorry. Here there's going to be A1n times the corresponding minor, M1n. That's better. Clear? That's the general definition of a determinant. Okay, so do you agree that calculating determinants involves a lot of calculations? Because even for a 3 by 3 determinant, we had to calculate 3 2 by 2 determinants. So if you want a single 4 by 4 determinant, it's going to involve 4 3 by 3 determinants. Okay, so calculating determinants requires a bit of work. Okay, so that's one comment that I want to confess to right now. Calculating determinants is a bit of work. There are some things we can do, which we're going to gradually see, that make it easier. Okay, but we haven't discussed them yet. Another comment that I want to make is that it has many applications throughout math and beyond. You mentioned physics. I mentioned earlier the notion of the Jacobian, which is something you use in multivariable calculus for changing variables. And if the words don't compile yet, they will when you get to multivariable calculus. Okay, it's used, for example, in geometry. Okay, if you want to calculate the volume of a parallelepiped made up of 3 vectors, that's what you use, a determinant. Okay, so you'll see these things show up, and once you see them, you'll say, hey, we know determinants, we know how to do this. Okay, but I'm not gonna, in this course, it's beyond our scope to show you all these applications. Okay, we're only gonna do it in the abstract realm of algebra and vector spaces and matrices that we deal with in this course. Okay. Okay. So here are some theorems. So here's our first theorem. And remember, I'm really not going to prove anything about determinants. The proofs are sometimes rather ugly, involve a lot of indices, and we're not going to do this. We're really only surveying the topic, really.
We should technically be able to do that, though.
Not if we don't do this stuff in class. So if we don't do any proofs in class, it would be unfair to ask you to do one at home, right? So answer, in general, no. Okay? Okay, so here's a theorem. The determinant of A transpose equals the determinant of A. This requires proof. Okay? It may not be obvious at all, but it's a fact. Okay? So if you take a matrix, find its transpose, that's simply saying that take the columns instead of the rows, right? Do you understand what I'm doing? You see columns? That's doing the transpose. The determinant doesn't see that. The determinant is a number, right? The determinant of a matrix is a number, is a scalar. Do you agree? And that scalar cannot sense this operation of taking a transpose. You get the same thing, okay? I'm not proving it, but I do recommend to convince yourself just by taking the 3 by 3 matrix that we did in the example, 1, 2, 3, 4, 5, 6, 7, 8, 9, taking its transpose, calculating the determinant, seeing that you get the same thing. Okay? A corollary of this is that any property of the determinant that talks about rows would be the same property about columns. Do you agree? So if we have a statement, for example, that if two rows are the same, the determinant is 0. I didn't just make that up. There's going to be a statement like that. If we have a statement that if in the matrix A, if two rows are the same, the determinant is 0, then automatically we know that if two columns are the same, the determinant is 0 because we take the transpose. Do you agree? Okay. So every property of A which is true for rows, and we're going to see several of these, is also true for columns. This is very different than, for example, what we had about row operations and column operations. Row operations can give you something completely different than if you do column operations, right? But as far as the determinant goes, things you do to rows and statements about rows in the determinant translate to statements about columns in the determinant. Okay? Good? Okay. Great. Here's another theorem. And again, there's theory hiding here, which we're not proving. Personally, I feel a bit uncomfortable doing what I'm doing now, just throwing theorems at you and asking you to believe me without giving you anything to cling to. Okay, but that's what we're doing here. Okay, life is a bit about compromises. Okay, so theorem, it has, no, let's write it as one theorem. Okay, so theorem, one can evaluate the determinant starting, even the statements, or not starting, using or by any row or column. Let me explain what I mean by this. Okay, even the statement is not very precise, but I want to explain what I mean. So when we defined the determinant, we said, take the first row, and then do A11 times its minor, minus A12 times its minor, plus A13 times its minor. What this theorem says is that you don't need to start with the first row. Take the seventh row and do the same thing. You'd get the determinant. So take A71 times its minor. Cross out row 7 in column 1. Minus A72 times its minor. Plus A73 times its minor, ... You'd get the same thing. Moreover, you can do it using a column. Take the fifth column. Take A15 times its minor, minus A25 times its minor, minus A35 times its minor. Any row or any column you take and do that procedure, you'd get the same determinant. Okay? With one little thing you have to pay attention to, so let's just mention it here. If we use an even row or column, we use the second row or the sixth column, an even row or column, we have to start with a minus. And if we use an odd row or column, like we did when we used the first row, then we start with a plus. And then do plus minus, plus minus, plus minus, always. Okay? So this again is a theorem, we're not proving it. The formal proofs of this stuff goes through, maybe the easiest way is to define the determinants slightly differently than the way we did, but I'm not going to do this. Okay? Okay, let's do an example of this theorem. An example. Let's take this exact example over here on this board. Remember that we got 0. We got 0 when we developed it, when we evaluated the determinant using this row. That's what we did. Right? Let's do it differently now. I'm going to erase this. Oops. I'm going to erase this, and I'm going to calculate it again. But this time I'm going to use not the first row, but rather maybe the second row. Or maybe let's use the second column. Okay, let's use this. Now I'm going to use this. Okay, so let's see what we get. What sign do we have to start with? Minus, because it's an even column. So we start with minus 2 times its minor. Its minor is 4, 6, 7, 9. Do you agree? Plus 5 times its minor. Cross out this row and this column. The minor is 1, 3, 7, 9. Right? Everybody with me?
Yeah.
Minus 8 times, cross out the row and the column, 1, 4, 3, 6. Do you agree? Okay. And again, let's carry out the calculation. So it's minus 2 times 36 minus 42, so it's negative 6, right? Plus 5 times 9 minus 21, negative 12, minus 8 times 6 minus 12, negative 6. Good? So what do we get? 12 minus 60 plus 48. And indeed, we get the same thing. We get 0. In a total, stemming from totally different numbers, right? Okay. So this is just to convince you, by means of an example, that the theorem is not, is sensible. It works, but that's obviously by no means a proof. Okay. So that was a theorem, but now we can write a recommendation. Let's call it. Recommendation. So suppose somebody gives you a giant matrix and you want to find the determinant. So let's call it advice. Right? We had theorems, we had corollaries, we had lemmas, we had examples, proofs. So far we didn't have advice. So here's advice. Evaluate the determinant. Not by the first row. That would be very doing it in a stubborn way, not in a wise way. Use the row that has as many zeros as possible. Right? Evaluate the determinant using a row or a column with as many zeros as possible. right? Because then most of these calculations are going to start with 0 times something, plus 0 times something, minus 0 times something. That's easy to calculate. Even I can do that. Okay? So here's an example. So let's do a 4 by 4 example, but a cheating one. So 1, 4, 0, 3, 1, 0, 0, 3, 1, 2, 0, 1, 1, 0, 5, 3. I want to calculate this determinant. What would I choose?
The third column.
Right, the third column. That's, it kind of sticks out as having the most zeros, and therefore the easiest calculation. So it's the third column, so it's going to start with a minus. I'm not even going to write down. It's 0 times, or let's say it's, no, third column starts with a plus, so, sorry. 0 times this 3 by 3 determinant, 1, 0, 3, 1, 2, 1, and 1, 0, 3. But I don't care what it is, because it's 0 times that. Minus 0 times another 3 by 3 determinant, plus 0 times another 3 by 3 determinant, and then the only one that survives is minus 5 times the corresponding determinant. 1, 4, 3, 1, 0, 3, and 1, 2, 1. Do you agree? Good? So this is the wise choice, whereas if you chose, for example, the first row, you would have 3, well, you'd still have 1 0, but you'd have 3 3 by 3 determinants to calculate. That's more work. Okay? What do we get here? Again, I have to choose a row or a column. So, for example, I can choose, obviously it's better to choose the second row or the second column, right? Because they have a 0, so let's choose the second row. And the theorem tells us you can choose whatever row or column you want. Okay, so I get minus 5. This I have to carry over. And then 1 with a minus, right? It's an even row, so I have to start with a minus sign. So it's minus 1 times this determinant 4, 3, 2, 1. Plus 0 times a 2 by 2 determinant, which I don't care about, minus 3 times the determinant 1, 4, 1, 2.
Take out all the minuses.
Do you agree? Good? And now I'm only left with 2 by 2 determinants, whereas a priori in this matrix, I would have 4 3 by 3 ones, each one having 3 2 by 2 ones. I would have 12. Right? So out of the 12, I only need to calculate 2. So let's see what we get. So I have negative 5 times negative 1 is 5 times 4 minus 6 times negative 2. Negative 5 times negative 3 is plus 15 times 2 minus 4, negative 2. So I have minus 10, minus 30, I get minus 40. Yes. My paper says it's correct. Clear? Okay, so is the advice clear? Okay. So what I want to do next is start collecting some rules for calculating determinants. Okay? So for example, what happens if you switch 2 rows? What happens if 2 rows are equal? What happens if you multiply a row or a column by 7? Okay, so we're going to collect all this information. We'll do it in a separate video.